In this video, we will prove the Pythagorean theorem. Now, while there are many ways to do so, this video will cover what is in my opinion the simplest proof. I will get to some of the other proofs in future videos. But before we get to actually proving the Pythagorean theorem, we must define what it is. The Pythagorean theorem states that if we have a right triangle, that is a triangle with a 90-degree angle, and we call one of the legs A, the other leg B, and the hypotenuse C, then the sum of the squares of the two shorter sides, or the two legs, in this case A squared plus B squared, equals the square of the hypotenuse, C squared. Now what does the Pythagorean theorem allow us to do? The Pythagorean theorem allows us to determine the length of any side of a right triangle if we are given the lengths of the other two sides. Let's say we have a right triangle, and this right triangle's hypotenuse is 5. This right triangle's hypotenuse is 5, and one of its legs is 3. This is the unknown, and we want to calculate the length of this remaining side, which we can call b. By the Pythagorean theorem, the sum of the squares of the two shorter sides, so in this case 3 squared plus b squared, equals the square of the hypotenuse, the longest side, 5 squared. 9 plus b squared equals 25. B squared equals 16, and thus b equals 4. B squared equals 16 gives you two solutions, plus or minus 4, but because length cannot be negative, we're going to disregard the negative solution. I'm sure many of you can do this type of calculation with ease, but the reason you came to this video was to see why this works, why the Pythagorean theorem works, and to answer your question, let's get to the proof. In this video, we will prove the Pythagorean theorem. In order to do so, let's start by drawing ourselves an initial right triangle. Let's name the longer leg A, the shorter leg B, and the hypotenuse C. Now the thing we want to prove here is that A squared plus B squared equals C squared. In order to do this, let's start by drawing ourselves a square of side length A plus B. So here's our square, and this square's side length is A plus B. Now, let's break up each of the sides of the square into their individual portions. That is the portion that is A and the portion that is B. And we can do this by drawing ourselves tick marks B distance away from the corners of the square. And thus we know that this distance, the distance from the corner to the tick mark, is B. Now because the whole side is of length A plus B, we know the remainder portion must be A. Now, if we connect the tick marks that we have just drawn, you'll notice something interesting happens. You'll notice that this triangle we have right here is identical to the triangle we drew in white on the left initially. We must remember that the angles on the exterior shape on the figure on the right are 90 degrees, because this exterior shape is a square. This triangle and the triangle on the left both have a longer leg of A, a shorter leg of B, and thus we can call the hypotenuse of this triangle C. The next step in our proof is proving that this interior shape is a square, and this will become important later on in our proof. Let's start by returning to our initial figure. Let's say the angle opposite of A is x, and the angle opposite of B is y. A statement we can make is that x plus y plus 90 must equal 180. And this is because the sum of the angles in a triangle must always equal 180. If we subtract 90 from both sides, we get x plus y equals 90. Returning to the figure on our right, the angle opposite of A is x, and the angle opposite of B is y. Now the angle we're interested in right now is this angle, which we'll call z. If we zoom into our picture, right over here, this is what we have. This angle over here is y, this angle over here is x, and this angle, the angle we are interested in, is z. We know that x plus z plus y must equal 180 because this is a 180-degree angle. We know that x plus y equals 90 from this statement over here, and thus we can say that 90 plus z equals 180. Subtracting 90 from both sides, we get that z is 90. Now what this tells us is that the interior angles of this inner shape over here are 90 degrees. Now we are certain that this inner shape is a square because all of its sides are of equal length, they're all c, and all of its angles are equal at 90 degrees. And this will allow us to move on to the next step in our proof. And this step involves making an observation about areas. And that observation is that the area of the larger square, that is the square of side length a plus b, is equal to the area of the four triangles, the four identical right triangles in this figure, plus the area of the inner square, the square of side length c. And now, what is the area of the larger square? Well, the side length is a plus b, thus the area must be a plus b whole squared. Now for the area of the four triangles, well, there's four of them, so if we take 4 and multiply that by the area of an individual triangle, we should be able to account for each of them. The formula for the area of a triangle is base times side over 2, and so the formula for the area of any of these triangles must be a times b over 2. Now this is the formula for the area of one triangle, and if we multiply that by 4, we can account for all 4 of them. Now here's where our proof that this interior shape is a square comes into play. If we didn't know that this was a square for certain, we wouldn't know how to calculate its area. We know its area must be c squared because its side length is c. Now, if we expand the term on the left, we get a squared plus b squared plus 2ab. Expanding the terms on the right gives us 2ab plus c squared. You'll notice that the 2ab terms cancel, and what we're left with is a squared plus b squared equals c squared. And thus we have proved the Pythagorean theorem.